Here in this video, we are solving two simple questions, theoretical, on semiconductor devices. The first question says, for a p-type semiconductor material, which of the following statements is true? So even before reading that statement, we shall try to know what do you mean by a p-type semiconducting material. We shall first of all remember back that semiconductors are of two types. One is extrinsic, means a pure semiconductor material whose number of electrons equal to number of the holes. It will pass the current only when you raise the temperature after breaking off some of the bonds. The typical examples of this pure semiconductor materials are made with silicon or germanium that has 4 valency electrons. So a typical semiconducting materials atom has 4 valency electrons that has a bonding with another 4 of the neighboring semiconducting material. It will pass current only when you heat it up. Now what people have done is, as we cannot heat up materials every time, they have added some kind of impurity to the semiconducting material called doping. Doping can be again done in two ways, that you can add either a trivalent impurity or you can add a pentavalent impurity. Trivalent means that has 3 valency electrons, pentavalent means that has 5 valency electrons. So when you add somebody neighboring with 5 valency electrons, say for example 1, 2, 3, 4, 5, these 4 will be forming bonds with the impurities, but the fifth one becomes free, has excess free electrons, thus it becomes an n-type material. The other possibility is you add a kind of another impurity called something like trivalent impurity. When you add trivalent impurity, you will add somebody who is having only, say, this is a semiconducting material with 4 valency electrons. Now you add someone with only 3 valency electrons, right? So these 3 will be having covalent bonds with the existing pure semiconducting material. The fourth ones has to make a pair with somebody who is not available there. Here is an empty space. That empty space is called something like a hole, the absence of an electron. Thus it becomes a more positive kind of a nature. Thus it becomes a p-type material. Thus the p-type material have a majority carriers of holes, and to get that p-type we shall add a trivalent impurity. N-type is the majority carriers of electrons. To get that we have to add 5 valency electrons, pentavalent atom. So the first option is the correct option. Holes are majority carriers in a p-type material and trivalent is the dopant. So that's as simple as a conceptual question itself, right? Let's have a look at the next question. In PN junction diode, the change in the temperature due to the heating is, so what happens in a PN junction diode is, this is p-type, this is n-type, this is the PN junction diode. There is a region called depletion region, which there is a potential barrier formed in this region which acts like an opposition to the flow of current, and that has to be broken for it to act like a conductor by conducting a diode in a forward bias. First thing is, PN junction diode is a material whose temperature coefficient of resistance is negative for semiconducting materials with which this PN junction diode material is made, like silicon and germanium. Negative means what? If temperature rises, its resistance is not going to increase, but its resistance is going to decrease. So the regular VI characteristic graph of a PN junction material who is something like this. Here there is a barrier potential, here there is a breakdown potential. So this is a VI characteristic graph, right? But This is the breakdown voltage, this is the barrier potential. But as the resistance, temperature varies, resistance of the device changes. As the resistance changes, the current in the both forward bias as well as the reverse bias will be getting affected. Thus, it affects the overall VI characteristics of PN junction diode is the right answer for the problem. That's how we solve these two simple theoretical questions on semiconducting devices. Thank you for watching.